what is the strength of the field at point 1 using figure 1? So this is figure 1. Okay. Choose your answers next week. Okay. So, this, I'm going to use my general picture that I use for all parallel plate capacitors. So for this, I'm going to draw a parallel plate capacitor like this, positive, negative, and I'm going to create this negative positive environment by using a battery of voltage V. In this case, I'm going to use a voltage of 40 volts. That way I just get this difference of 40 volts and 0 volts. Okay, and that's going to create an electric potential from both sides. This will be 40 volts over here. This will be 0 volts over here. And electric fields are drawn from leaving positives and going into negatives. So going out of the positive into the negative, this is going to be the electric field. And the formula, the relationship between electric potential, which is voltage, and electric field is electric field integral of E dot dx. In this case, the electric field is uniform because, did they tell us a parallel plate capacitor? It's going to be uniform because there's an even, it's proportional. They're all evenly spaced. So in this case, V is going to equal negative E delta X. All right, so what is the field strength at point 1? What is the strength of the field? So it's going to be uniform. The easiest way to do this is going to say, is we take V equals negative E delta X, and we know that it's going to be that because everything is uniform and evenly spaced. E is going to be negative V over delta X. In this case, I'm going to use these two, 10 and 0. And the difference between them is 1 meter, and the voltage difference is 10. And so the electric field is going to be 10, and it's going to be newtons per coulomb, but also we could use volts per meter. Volts on top, meters on bottom, volts per meter. They're both acceptable units for electric field. So this electric field is going to be 10. I'm going to use volts per meter just because we're given a graph with volts and meters. One other thing we could do, since it's uniform, is we don't have to use that point there. We could use any point. And so just for a concept here, we're going to do the endpoints here. So it'll be 40 minus 0, all over 4 minus 0, which is 4, which is also 10 volts per meter. So even though I use the ones closest, which is generally good practice just because you want to take the smallest, closest differential you can just to get the most accurate, but since it's uniform, it doesn't matter. All right, select the correct direction for the field at point 1. So this is basically going to go down to this picture I drew right here. The electric field is going to go from the positive to the negative, as we showed in this graph, basically this parallel plate capacitor, which is the same thing as this graph up here that we just created. It's going to go from right to left. So select the correct direction of the field at point there. It's going to be to the left. Yes, I'm good with that. So what is the strength at field point 2? It's uniform throughout the whole thing. We do the same thing. Delta V over M, 40 minus 30 is 10. 4 minus 3 is 1. So again, we get 10 volts per meter. What's the direction? Same direction. We're going to have it to the left. So the big point of this is recognizing that when you have uniform distance between a given differential voltage. So each of these has 10 volts between them, and they each have 1 meter between them. When you have that sort of uniform pattern, that's going to be the same as a parallel plate capacitor. And so it's easier to visualize it like this. And I try and draw out the picture when I can, if I have time. Another key idea here is that the direction of the electric field is going to be perpendicular to the equipotential lines, and the electric field is going to go from high voltage to low voltage. Which, when you look at the picture, it's like, okay, that seems reasonable. So, key concepts. Hope that helped. See you next time.